Welcome to the 8th lecture. We are studying low frequency responsive amplifiers, and in this lecture we will study the total low pass frequency response. In fact, we will summarize what we have been studying about the low frequency response of BJT amplifiers in our last lectures. Right. So we have studied that the low pass frequency can be set by the input coupling capacitor, the output coupling capacitor, and the bypass capacitor, and three different expressions to calculate each of these three items. So graphically we can represent the same on the body plot, on which we plot f, the frequency, on x-axis and the gain on y-axis, and we see that as we go below FCL, the lower cutoff frequency, the gain decreases by at a rate of 20 dBs per decade. But since one of these three FCLs computed from input coupling capacitor, the output coupling capacitor, and the bypass capacitor, one of these three would be the largest. Suppose this is the largest from the input FCL obtained from the input coupling capacitor. This is the largest, so the gain starts decreasing at minus 20 dBs per decade unless the frequency is equal to the cutoff frequency obtained using the output coupling capacitor. Now we have two capacitors, therefore the decrease is now minus 40 dBs per decade, and as the frequencies keep on decreasing and we get FCL due to bypass capacitor, the overall decay is then minus 60 dBs per decade. So it keeps on decreasing, but at first FCL this is minus 20 dBs per decade unless we get the second FCL, after which it becomes minus 40 dBs per decade unless we get the third FCL, after which it is minus 60 dBs per decade. So the fall is steeper than the fall was here, and the fall here is even more steeper than the fall it was here in this region, right? So this fall is steeper than this, and this fall is even steeper than this fall, right? To better understand the concept, let's solve an example. In this example we are given this BJT based amplifier. It's a voltage divider biased amplifier where the emitter resistor is broken into two parts. One of the emitter resistors is bypassed and the other isn't. So what we have to do is we have to compute voltage gain, and then we'll compute the FCL due to the input coupling capacitor C1, due to the output coupling capacitor, and due to the bypass capacitor. Let's see. But first calculate the gain. The gain is RC in parallel with RL divided by small re plus the part of re that is not bypassed by the capacitor, that is capital RE1. We won't include capital RE2 because it is bypassed by this bypass capacitor and isn't included in this expression to compute AV. We have studied this expression in our last course, that was electronic devices and circuits, EDC course. Right, so AV comes out to be 54 ohms or 34.3 dBs computed using 20 log of AV as a ratio. So let's compute FCL due to C1, and then from due to C3, and finally due to C2, the bypass capacitor. What is FCL due to the input coupling capacitor? We have studied the expressions in one of our earlier lectures. It's 1 over 2 pi Rn plus Rs time the input coupling capacitor C1. What is Rin? By looking into the base from the input side, we see R1 and R2 in parallel, and there is another thing in parallel, that is beta times the resistance of this junction plus the resistance that is not bypassed by the capacitor, that is capital RE1. So we write this expression as this R1 in parallel with R2 in parallel with beta times RE plus the portion of RE that is not bypassed by the bypass capacitor. Putting these values in, we get it to be 222 Hertz. And let's come to the output coupling capacitor. We studied the expression, that is 1 over 2 pi times RL plus RC sine times C3. Putting these values in, this is 50.8 hertz. And finally, let's compute FCL due to the bypass capacitor, namely C2. Here we studied that the resistance that is seen by looking into the circuit at this point is RE2 in parallel with RE1 plus this small RE plus this R1 in parallel with R2, and when taken on the output side they are divided by beta. We studied in last lecture. So we divide them beta plus RE plus RE1. This I forgot initially and I wrote it later, therefore you can hardly see this one, but it is there, RE1 in parallel with RE2, right? So plugging these values in gives us FCL due to C2 36 hertz. Now we have due to bypass capacitor 36 hertz, due to the output coupling capacitor 50.8 hertz, and due to the input coupling capacitor 282 hertz. This is the largest value. So putting this in the form of a graph, 34.3 dB is the gain in the midband gain. At this point this is 282 hertz because, and the roll off is minus 20 dBs per decade at this point, and at this point this is 50.8 hertz. The gain is now minus 40 dBs per decade because at this point we get the second 50.8 hertz we get the second circuit in action, the second RC circuit in action. Now we have two RC circuits and the roll is doubled, and now the roll is tripled at 36 hertz. 36 hertz is the third frequency that is caused by, it is the third cutoff frequency caused by the bypass capacitor. So this is how we plot the body plot. This is the body plot of this amplifier, of this BJT based amplifier. This is body plot. Frequency, the gain plotted versus frequency, and we see three cutoff frequencies here, and with each cutoff frequency the roll off is doubled. It's not doubled, it's multiplied by 2. It's minus 20 dBs, minus 40, and then minus 60. So we get another minus 20 dB per decade with each cutoff frequency, right? So here's a small exercise for students. We have to find AV at 141 hertz at a frequency that is 1/2 of the first cutoff frequency. You have to find the value of gain there, and you have to find AV at 50.8 hertz, the second cutoff frequency, and at the third cutoff frequency 36 hertz. This is left as an exercise for my students. That's all for this lecture. We'll meet in our next lecture with some more stuff from frequency response. Thank you.